the halogenation reaction. So first one will be halogenation, where halogen will be added. So if I take phenol and add bromine, but the solvent is aqueous in nature, in that case we will get a product like this. We will get 2,4,6 tribromophenol. It's a white precipitate. The name is 2,4,6 tribromophenol. So the substitution will occur at the 2 ortho position and 1 para position. Why? Because this phenol is already activating the benzene ring. Now in presence of water or in aqueous solvent, the ring is highly activated. The ring is highly activated, so the substitution is taking place at the 3 positions where the electron density is maximum in the resonating structure. Now if I want to get monobromophenol, so if I want to get the bromine in 1 position, that means mono substitution. In that case, to this phenol I will add bromine, but in place of aqueous solvent I will take carbon disulfide. So I will get, so if I take carbon disulfide, which is a non-polar solvent, in that case I will get one ortho substitution, another one is para substitution. So if I am using aqueous solvent, the solvent is aqueous in nature, and performing this halogenation reaction, we will get the product which is substituted at 3 places. But if we change the solvent to carbon disulfide, in that case the substitution will take place at 1 position, at para or ortho. So we will get 2 products, one ortho, another one is para. Now in case of this carbon disulfide, when we are using non-polar solvent, the ionization is to a lesser extent. In this case the ionization is higher. In this case the ionization is lower. So the substitution will take place at ortho and para position, and 2 different products will be formed. Not substitution at 3 positions simultaneously. So in this case, when we are using aqueous solvent, the ionization is occurring to a larger extent. And when we are using carbon disulfide, a non-polar solvent, the ionization is occurring to a lesser extent. So we will get the substitution, so the substitution is limited at 1 position. Okay, so the substitution will not take place at the 3 positions. So we will get ortho as well as para product. Now we will see the nitration of the benzene ring, where nitric acid is used and the nitro group, that is NO2 plus acts as the electrophile. So let's see nitration. Now we will see the nitration. Second one is nitration. Phenol, on treating with fuming nitric acid, we have seen that nitration takes place in presence of concentrated nitric acid and concentrated sulfuric acid, and in that case this is produced, which is substituted in the benzene ring. Okay, but in case of nitration, if I treat phenol only with concentrated nitric acid, in this case again substitution will take place at the 3 positions. This is 2,4,6 trinitrophenol. In the previous case, we have seen when we were adding bromine water, it was forming 2,4,6 tribromophenol. But in this case, we will get 2,4,6 trinitrophenol, and this is called picric acid. So this is picric acid. But if I want to limit the substitution at one position only, in that case, I have to use dilute nitric acid, where one ortho product will be 4 and one para product will be 4. So this will be the major product. 30 to 40% of this para product will be formed. This is somewhat lesser in percentage. So this is the nitration of phenol, where we can get this kind of products. In the same way, sulfonation can be done using concentrated sulfuric acid, where sulfonic group acts as the electrophile. So let's see the sulfonation. Now the third one is sulfonation, where we can use concentrated sulfuric acid. So if I use at a temperature of 298 Kelvin, in this case we will get only the ortho product. At a low temperature we will get only the ortho product. But if I increase the temperature to 373 Kelvin, in that case we will get the para product. Clear? And if we heat this phenol with concentrated sulfuric acid and we continue prolonged heating, in that case we will get ortho and para substituted. For example, to this phenol, if I add concentrated sulfuric acid and continue the heating, in that case we will get ortho and the sulfonic group at ortho as well as at para position. So this is the sulfonation of the phenol. Next we will see the Friedel-Crafts acylation as well as alkylation. In case of alkylation, methyl group is substitutes the hydrogen, and in case of acylation, acetyl group substitute the hydrogen. So the next one is Friedel-Crafts alkylation, where the reagents that are used are, number 1 is methyl chloride and number 2 is anhydrous aluminium chloride. This aluminium chloride acts as the Lewis acid and produces the electrophile methyl. This is what is produced as the electrophile. So, if I take phenol and add methyl chloride, anhydrous aluminium chloride, in that case we will get ortho product. So it is 2 methyl phenol and a para product. This is 1, 2, 3, 4. 4 methyl phenol. Okay. So this is Friedel-Crafts alkylation. Now if I talk about acylation, in that case, now in case of acylation, anhydrous aluminium chloride is okay, but here we take acetyl chloride. So this is the reagents that we use. So here Cl. So in this case we will get a keto product. So this carbon, the carbon which is attached to halogen, okay. So this carbon will attach to the benzene ring and we will get a keto product. Same here. So this is Friedel-Crafts alkylation and acylation. Mainly this process of this alkylation acylation, the yields are generally very poor. Okay, so alkylated phenols are not easily obtained. Now, so this is all about the substitution of different compounds or functional group in the benzene ring of the phenol at the ortho and para position. Now we will see few named reaction, famous reaction which involves phenol, and that give rise to a different product.